Hey everyone, welcome back to Abstract Algebra 1. This will be lecture 5 of the course. And in this section we're going to continue with our group properties and descriptions and theorems, etc. This is going to be a section called Finite Groups and Subgroups. So we're going to get into a little more detail about some examples of finite groups and some of the terminology and concepts surrounding finite groups. And then we're going to define a subgroup and go through a series of theorems related to subgroups and the identification of subgroups. So let's go ahead and jump into it. We're going to call this section 2.3 Finite Groups and Subgroups. All right. So as we'll see, the finite groups, basically just groups that have finitely many elements. Finite groups have some very, very interesting properties, particularly arithmetic properties. And so we're going to be exploring those throughout this lecture. And the way to start the course, we're going to need some terminology as we proceed, but the way to start is really with the idea of the order of a group. Okay, so we'll start with this definition. And this is the definition of order. So the number of elements of a group, is called we'll say is called its order. Okay. So the number of elements of a group is called its order. Okay, so kind of like polynomials in algebra will have an order. Say the order of a polynomial has to do with the highest exponent, the largest exponent of the polynomial. In group theory, it's a little different. The order of a group has to do with the count of the number of elements in the group. Right? Now, the order of a group can be finite, obviously, or infinite. Okay, and for the notation, we use the notation, this notation, to denote the order. Okay. Let's see an example or two here. So the integers under addition, right? We saw this group, the integers under addition. Obviously, the size of this group, the order of this group, is infinite. Right? So we could say the order is infinite. Okay, right? Every integer is in the group, so it has infinitely many. Let's talk about a finite group. Let's see an example of a finite group. And this is one I don't think we've talked about yet, but let's get this one out because we'll use it a lot. So the group, and we're going to denote it U10. And in this case, U10 is the elements 1, 3, 7, and 9. Okay, this is U10 is the group which is basically this set under multiplication modulo 10. Is this set under multiplication and then modulo 10. In this case, that's what the 10 means in the parentheses. Okay, so we call that U10. And as you can see, the order of U10 is 4, right? There's 4 elements in the group. Now, what does this group do? We'll use this group a lot. So the idea is that all of the elements in this group, if you multiply them together and take the result modulo 10, you'll note that you have closure here. So for example, 1 times 3 is 3, which is in the group. 3 times 7, how about that one, is 21, which is congruent to 1 modulo 10, which is in the group. These are the group elements, right? We're just reading them back to ourselves, right? And we could keep going. 9 times 7, anytime you multiply any of these 4 elements. So 63, that's congruent to 3 mod 10. Let's see, 9 times 3, 27, that's 7 mod 10. Right? And you may be able to find others. Right? And so that's the idea with U10. And it's obviously a finite group, has 4 elements, and therefore the order of the group is 4. etc. here. Okay, so that's the definition of the order of a group. Now we can also talk about the order of an element of the group. Okay, so another definition that we'll need. The order of an element, and we'll say G in a group G, is the smallest positive integer n. It's the smallest positive integer n such that G raised to the nth power is E. Now, the way to think about that is it's G multiplied, whatever the group operation happens to be. In the case, in using this notation, the implication is that we're talking about multiplication, right? So G times G we would denote as G squared. G times G would be G cubed, etc. Right? So the smallest positive integer such that G to that raised to that power is equal to the identity. Now, you should also think about what this means in additive notation. So in additive notation, we would be adding G to itself. And so instead of this notation, we'd want to opt for something like this, n times G. Right, so G plus G, in that case, that's 2 times G, 2G. G plus G would be 3G, etc. Okay, and so whatever this integer n happens to be, that is what we call the order of the element. Right, so it's kind of like, how many times do I have to repeat the operation on an element to get to the identity? Right, that's kind of a simple way to think of it. How many times do I repeat the operation until I get the identity? Right, now in some cases, you'll never get the identity. So if n does not exist, we say that the order of the element is infinite, right? Meaning it never squares with the identity. Okay, so let's see some examples of this definition. This one's a little bit more unusual. I mean, the order of a group is straightforward. It aligns with the cardinality of a set. That concept is very, very clear to us probably. Let's take a look at this example. So let's consider U15, right? So this is the multiplicative group modulo 15. Okay, so we can enumerate the elements. Now you could figure out what the elements are just by using modulo 15, but I'll just write them out here and we can sample from this. 1, 2, 4, 7, 8, 11, 13, and 14. Okay, so these are the elements of U15. Right, and so from this you can see that there are 8 elements. So the order of U15 is 8. What about the order of the elements themselves? So let's take a look at the order of the element 7. So 7. So let's see what happens here. So I have 7 to the first power is 7. Okay, obviously in the group. 7 squared, so 7 times 7 equals 49, which is congruent to 4 mod 15. Okay. 7 cubed is 343, which is congruent to 13 mod 15. All right, you can figure this out just by taking 343, dividing it by 15, and identifying the remainder. Use the division algorithm on 343. Okay. What about 7 to the 4th power? Well, that one, it turns out, is 2,401, and which is congruent to 1, right? And so this is the key right here, right? So 7 times 7 times 7 times 7 is 1 mod 15. So the order of 7 is equal to 4. So n is 4 in this case, 7 to the 4th power. Okay. What about, let's try another one. What about the order of 11? 11's in U15. How many times do I have to multiply 11 against itself to derive the identity? Well, 11 to the 1st power is 11. That's not it. 11 squared is 121, which happens to be congruent to 1 mod 15. Okay, and so just like up here, that meant that the order of 7 is 4. Here, the order of 11 is 2. Okay. Now you could go through this, and I'll list out some of the other values for you, and you can take a look and see if you can confirm this. So the order of 1 in this group is 1. I think that's probably the case most of the time for these, right? The order of 2 is 4, and so that means 2 to the 4th is 1 in this group. The order of 4 is 2. Okay, I mean, that makes sense. 4 squared is 16, which is 1 mod 15. The order of 8 is equal to 4. The order of 13 is equal to 4 as well. And then the order of 14 is equal to 2. All right, so you could confirm some of these other values. So that's an example of the order of an element using a multiplicative group, a group where the binary operation is multiplication. What about addition? Let's do an example with addition. Sometimes people can get a little tripped up when they try to move between the operations. So let's take a look at this one. So let's consider z10. So there's the integers modulo 10. So this is addition modulo 10. Okay, and so let's look at what about the order of 2? Well, so remember, so 2 times 1 is just equal to 2. Okay, so that's not it. What about 2 times 2? That's equal to 4, so that's not it. Again, we're modulo 10. What about 3 times 2? That's 6, not it. 4 times 2? 8. Okay, what about 5 times 2? 5 times 2. That's 10. Now 10 modulo 10 is 0, and that's the identity in this group, right? The identity of in Z10 is 0. We're talking about addition here. Okay, so that means that the order of 2 is equal to 5. Now you can kind of visualize this a little bit. I don't know if this is super helpful, but I'm going to write it out anyways. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I like to space those out equally, but let's see if I can do a little better. That's a little better. Okay. All right, so I start at the identity, and I hop to 2, right? And then I hop to 4. Then I hop to 6, right? So starting at 0, and then I go to 2, 4, 6, and then I hop to 8. And then I hop to 10, right? So 1 hop, 2 hops, 3, 4, 5. The order is 5. Okay, so that's how you could visualize the order of the element 2. Like how many times you have to repeat the operation on the element to get back to the identity. Let's do another example out of this group. What about the element 4? So what about the order of 4? Okay, so similar to before, we'll say 1 times 4 is 4, 2 times 4 is 8, 3 times 4 is 12. Now 12 is congruent to 2, mod 10, right? And then we would say 4 times 4, that's 16, which is congruent to 6 mod 10. How about 5 times 4? That's 20, which is congruent to 0. Right? So again, here we'll go to 5. Right? So the order of 4 is equal to 5 because I have to do it 5 times to get to my 0. So let's see what that looks like visually here. So this is again modulo 10. 1, 2, 3, 4, 5. Okay, so we start here. So this time we'll start at 0 again. And the element is 4, so I hop to 4. Then I hop to 8. And then I hop to 2. And then I hop to 6. And then I hop to 0. And so it's got this nice pattern. And so you can see that's 1 hop, 2 hops, 3 hops, 4 hops, and then another one would be 5. All right. And so the order of 4 is 5. Okay, so that's the order of an element. And then, I mean, these are kind of fun to play with. It's fun to kind of exhaust a group like this and see what all the patterns look like. You know, see some of them maybe. I don't recall off the top of my head modulo 10 what happens to all of these. So you could try and see if everything between 0 and 10 has a finite order. All right, let's move on. So those are a little bit like some prerequisite concepts for the subset notion. And so let's define a subset next. Oh, sorry, a subgroup, not a subset. If a subset H of a group G is itself a group under the operation of G, is itself a group under the operation of G, we say that H is a subgroup of G. All right. So if you've got a group G and you can identify some subset of G which is itself a group, then you have yourself a subgroup. Very similar to the idea of a subspace from linear algebra. Real similar concept here. So you've got a vector space and you've got some subset of the vector space which has all the properties of a vector space, just happens to be happens to be contained inside of another vector space, then that's a subspace. And so the subgroup concept is very similar. Okay, and so we're going to use some notation. It might come up, probably not today, but it'll come up later. We'll use H is a subgroup of G. We'll use this notation for that. Now in this case, the implication is that H may be the same as G, meaning it may have all the same elements as G. If H is indeed a proper subset of G, we'll use the notation like this. Okay, so this means literally H is a subgroup of G, right? In this case, H is a proper subset of G as well. Okay. Now, another thing to notice here is that, and you can confirm this pretty easily, the subset that contains just the identity is always a subgroup. It's called the trivial subgroup. In typical mathematics convention, we'll call it the trivial one. It's always there. There's always that subgroup for sure. Okay. Now, it's not always as straightforward as you might think, identifying and determining whether or not a particular thing happens to be a subgroup. So what we'll do next is go through a series of tests that can be used to make a determination as to whether or not some subset you're looking at rises to the level of a subgroup. Okay, now you could always just do it the old-fashioned way and prove all the properties of the group hold for the subset, and that's fine. But some of these tests can expedite that process somewhat. Right, and so we'll start with this test. And what we're going to end up doing is kind of daisy chaining some of these theorems together. So this one will be the most difficult, I think, to prove. And the others will kind of rely on this a lot for their proof. All right, so this one, we'll call this the one-step subgroup test. It's actually got several steps, but it's got one key ingredient here. All right, so for this one, we're going to let G be a group and H a non-empty subset of G. Okay. And so the theorem says that then if, well, so then H is a subgroup of G if A, B inverse, right, or A minus B in additive notation, right? So if A times B inverse is in H whenever A and B are in H. Okay, right? So straightforward. It may not be obvious why this is true, but all this is saying is that, hey, if I have some subset of a group G, and if I can show that whenever A and B are in the subset H, then the product A times B inverse or A minus B in additive notation, if that product or difference is in the subset, then I've got then that subset is actually a subgroup. Okay. All right. So that it's called one step because it's really just like this one thing that you have to verify. Okay. Now there are more than one steps when we use this actually, but it is the idea is that we just do have this one thing to verify. So let's go ahead and try to prove this. Okay, let's prove this theorem. All right, so there's going to be a couple steps here that we'll look at. The first thing to look at is the associativity question, the associativity of the operation, right? And that one we get for free. The operation of, H plus or H whatever the operation happens to be is the same as the operation of G plus. And obviously all the elements you'd be applying these to are in H, which happen to also be in G. And so you get associativity for free. Right. That's great, right? Because, I mean, look, if G is a group and this is the same operation being used on a subset of G, then obviously if it's associative for G, it's associative for the subset. Okay, so we get that one for free. Okay, so then the second thing we got to look at is this question of the group status, right, beyond that. So we'll start by showing that the identity must be in H. Okay, so we'll start with that. Got to prove the rest of the group properties. So to see that E is in H, let's let X be an element of H. Okay. Now what we're going to do is, so up above here we have the AB inverse. We're going to be using that notation. We'll assume this is a multiplicative group. Okay. And so what we're going to do is we're going to let A equal this X, and we're also going to let the B equal X. Okay, in our hypothesis up here of the AB inverse. If A and B are in H, then we're going to show that AB inverse is in H. Okay, so we're going to let A equal X, and we're going to let the B equal X. Right? We're just assuming X is some element, and we're saying A and B are the same. Right? So i.e. A and B are the same element. And we'll see that just assuming this is enough to show that E is in there. Okay, so then E is equal to X times X inverse. We know that. That's just X times its inverse is automatically equal to the identity. And since X is equal to A and B, that's equal to A times B inverse. So it's an element of H. Okay. Now, one thing we've used here that might be cheating a little bit is we've assumed implicitly that X inverse is part of H. So how do we know that X inverse is in H? Well, let's prove that one next. We'll say, let's let A equal the identity, which we know is in H, and we'll say B is equal to X, right, which we've assumed X is in H. Right, then, by assumption, AB inverse is in H, right, and that's going to imply that E times X inverse, which is obviously just X inverse, is in H. Right, so you get that one for free by assumption. All right. Okay. Now, the last thing to show is that H is closed. We need to show closure. The last thing to show is that H must be closed. So for this, we're going to let X and Y be elements in H. So if X and Y are in H, we know that Y inverse is in H. From this argument right here. So we know that Y inverse is in H. Okay, so let's let A equal X and B equal Y inverse. And what do we get then? Well, so we have that AB inverse is in H. So therefore, AB inverse equals X times Y inverse inverse. Right, we're just letting B equal Y inverse here, which is equal to, of course, X. The inverse of the inverse is just Y itself, so it's X times Y, and that would be in H. Right, since AB inverse is in H, then whatever AB inverse is equal to must also be in H. Okay. All right, and so we have closure. So we have the identity, we have associativity, we have the identity in the subgroup or the subset, we have that inverses exist in the subset, and we have that the subset is closed. So those are all the properties that are required for a group, right? And H is assumed to be just a subset of another group G. It inherits the operation. That's where the associativity comes from, right? And so there we are, the one-step subgroup test. So all we need to show is that take any two elements of the subset and show that the product of A and B inverse is also in the subset. Okay. All right. Very good. Now what we're going to do is we're going to do an example, walk through how this is done in practice, like with a real group and subgroup. Okay, so let's do an example and we'll walk through how this can be used. So let's let G be an abelian group. Which one doesn't matter, but just so long as it has that property. So we'll let G be an abelian group with identity E. Then H is going to be our subgroup, and we're going to define it like this. X is in the group G such that X squared H is equal to all of the x's in G such that x squared is equal to the identity. Okay, and so this H is a subgroup of G. So how can we prove this? Okay, how do we want to? How can we use the previous theorem, i.e., the one-step subgroup test, to see that this is indeed a subgroup? Okay, so how to use the one-step subgroup test. We'll just go through this as kind of a working example. All right, so the first thing you want to do when you're doing this is you need to identify the property that distinguishes the subgroup from the larger group. So identify the property that distinguishes the subgroup from the larger group. So in this case, distinguishes H from G. Right, and so in this case, in the case of the example we're working, that property is that the group element squared needs to equal the identity. Okay. Right, that's what it says right here. That's how H is defined. It's every element where when you square it, it is equal to the identity. And then what you want to do with that, then, with that property, is you want to use it to prove, that the identity also has this property. Okay, so in this case, right, this is very straightforward. You simply say, hey, look, E, when I square it, is equal to E, right? So the identity times itself is E, right? So that's obvious. And so that's going to tell you that, first of all, the subgroup contains the identity. And second of all, it's going to tell you that the subgroup is not empty. Well, so E is in H, and therefore E is not empty. Or sorry, H is not empty. Sorry about that. H is non-empty. Right, like that. Okay. All right. So, and then the third thing to do is to assume two elements have this property, i.e., that two elements are in the subgroup, and then to use this assumption to show that A times B inverse is also has this property. Right, so assume two elements have this property, and show that AB inverse does as well. So when I say two elements, what do I mean? A and B. Right, A and B. Assume two elements A and B have this property and show that AB inverse has the property as well. Right, and so obviously if you show that AB inverse has this property, that implies that AB inverse is in the subgroup as well. Right, and so there you've showed that whenever A and B are in the subgroup, AB inverse is as well. Okay, so let's do that for our case. So in this case, right, we'll let A, B be elements of H. And so that, what does that mean? A squared equals E equals B squared. Okay. All right. And so what we can do then is we can just, we have this fact, right? And we can just look at AB inverse. Okay. So AB inverse, and in this case, we want to look at AB inverse squared. Okay, and we want to show that this must be equal to the identity. Well, this is just equal to AB inverse times AB inverse. Okay. Now, it's important that we recall that the group is abelian, which means that every element in the group commutes with every other element in the group. So that means the A's and the B's and the A inverses and the B inverses and all that stuff, they all commute. So that means I can rearrange this to my heart's content and not change the element. Right, so in particular, it means that I've got A squared times B squared inverse. Okay. I think I want to write that differently. Sorry. Let me kind of let's do it this way. So I've got A squared, and then I've got B inverse. We'll write. What kind of intermediate step this? Okay. And so if I've got A squared and I've got B inverse times B inverse, that's really just B inverse squared, isn't it? Okay. Right, and all of this is fine because G is an abelian group. Everything commutes. And so then I can say it's a hop skip to A squared, B squared, inverse. I can just interchange those. And I know then that this is equal to A squared is E, and B squared is also E. And so I've got E times E inverse. I know that that is equal to E as well. Right? So that's the key here. So A squared equals E. So that fact and B squared equals E implies that AB inverse squared equals E. Right? So this is equivalent to saying that A and B elements of H implies that AB inverse is an element of H. So A comma B in H implies that AB inverse is in H. Okay, so this is a great example of using that theorem to prove something about a real group. Okay. And AB inverse in H, that's all we need. That's all we need to show that this is a subgroup. Okay, perfect. So that is an example of how to use the one-step subgroup test. So now I want to introduce another test, and this one is called the two-step subgroup test. We'll do a couple more of these, and I think the value of this will all begin. So the value of the first one is obvious because, hey, look, I mean, sometimes we need to figure out whether such and such is actually a subgroup, and here's a method to do it that doesn't involve proving all the properties of the group. Right, and sometimes you can't use the straightforward proof, and you have to rely on something like this. Right, now this next example expands on that, expands on the previous. Also going through these subgroup tests shows you something about how subgroups work, right? So in the previous case we saw that if we can merely prove the fact that if it's almost like we're proving a special case of closure, basically, right? Given A and B in the subset, AB inverse must also be in the subset. It's just a single special case of the closure property, really, and that's enough to prove a subgroup, right? We don't have to mess with associativity. We don't have to mess with all of the other little things as well, right? We don't have to show that the identity is there necessarily. We don't have to show that closure works in every case. We just have to show this one specific example. So let's talk about this one. So here we're going to let G be a group and H a non-empty subset of G. Then H is a subgroup. Right, it's a subgroup of G if A comma B in H. Oh, sorry, exactly backwards. If A times B is in H whenever A and B are in H. And so that's the first step, is to show that the product of two elements in the subset must be in the subset. That just is closure. And secondarily, A inverse is in H whenever A is in H. And so what is that? Well, that's like closed under inverses. So the first one is proper closure, right? So if I have two elements in the subset, if their product is in the subset, then I have closure. The second one says that if an element is in the subset, then its inverse must be as well, right? So that's closed under inverses, meaning if you get one, you get the other automatically. If you get A, you automatically get its inverse. So there's two things to show there, closure and closure under inverses. Okay. And so this is a really easy proof to use given the previous proof. We can crank this one out really quickly using the previous one. So really, using the previous test, we need only show that A comma B in H implies A B inverse is in H. Okay. And once we've done that, then we've proven the two-step subgroup test works as well. So we're going to let A B be in H. Now, since H is closed under inverses, right? We're assuming H is closed under inverses, then B inverse is in H. Okay. Straightforward. Okay. Then A times B inverse is in H. And that's just proper closure. Okay, that's just by closure of the operation. Okay. Right, so what have we done here? Well, in this proof, what we've done is if we assume that AB is in H whenever AB is in H, and A inverse is in H whenever A is in H, if we do that, if we assume those two things, then we get the property that we need for the one-step subgroup test immediately. Then AB must be in H if A and B inverse are in H. Okay. So this one is, I mean, the proof is immediate given the last step. Now in this subgroup test, what you just prove closure first, kind of separately. Sometimes that's really an easy thing to do. Sometimes it's not. If it is an easy thing to do, then this is the test to do, because the closure argument, if you can prove that, then the inverses usually follows quickly. Okay. All right, and we'll do some examples using this. But let's go ahead and let's talk about counterexamples. So sometimes we'll want to be able to show that a subset is not a subgroup. Right, and I'm sure people have seen this idea. I'm sure this is something people have seen, but usually if you're trying to prove that something doesn't rise to the level of something else, then all you need is a counterexample, and that's kind of the case here, right? So if we want to show that a subset is not a subgroup, there's a number of ways to do it. One of the ways to do it is to show that the identity is not in the subset. Show that E is not in H. Okay, so the identity is not there. You can do that. That's one option. Another option is to find an element whose inverse is missing from S. So you could show that there exists an A in H such that A inverse is not in H. Right, you could find some element that's in the subset whose inverse is not. And then the last option would be to show that closure fails. Show that there exists AB in H such that AB is not in H, right? So closure fail. Failure to stay within the subset. And we can do a quick example of this, right? This will be things you'll see. We're going to let G be the group. We've seen this group before. We're going to call it R star under multiplication. And so remember, R star was the non-zero real numbers, non-zero, so excluding 0. And this group is non-zero real numbers under multiplication. All right, and we saw that before that was a group. Maybe I'll write that. Non-zero reals under multiplication. Okay, and so we could define a subset H of R star. And we could define it such that X is a member of the group, i.e. it's a non-zero real, such that X is equal to 1. That way we can get the identity. Or X is an irrational number, i.e. X is not a rational number. X is not in Q. All right. And so this is a subset of this real number, non-zero reals, right? 0 is not a, yeah. So this is a subset. Well, we could easily show that it's not a subgroup, right? Let's take an example of one that's in here. So the square root of 2 is in H, right? But we can show that closure fails here. Because the square root of 2 times the square root of 2 is 2, which is not in H. Right? The square root of 2 is not an irrational number. All right, that's just a simple example. All right, so not just because something's a subset doesn't necessarily mean that it's a subgroup. All right. Let's see here. I think this might be a good place to pause. I think I'm going to, I'll break the video into 2 parts. So this will end part A here and pick up with the last subgroup test in part B. All right, see you in a moment.